Okay, let's keep going. And this show you the muscle fiber, and inside you have those microfilaments. We call them thick filaments, thin filaments, and together is create the myofibril. This the myofibril, and myofibril outside is covered by SR. So this blue blanket, these are the SR. So inside the SR, they have a lot of calcium. And when the muscle contraction happens, the calcium will be released from SR. It will go to the myofibril and create a muscle contraction. And this yellow net is called the T-tubule. T-tubule's function is quickly transduct electrical signal from the outside to the inside muscle fiber. Neurons ask muscle to contract, so you decide to move the skeletal muscle. The signal from the neuron will touch the surface of the muscle, and the signal will be transferred into the muscle's electrical signal, action potential of the muscle. And apparently when you contract the muscle, you don't want only the surface of the muscle to contract and inside relax, because that's the muscle you put your life on when you need to fight a bear or run away from the bear. You want all the muscle fiber be able to contract at the same time. So you need to have the network quickly transduct electrical signal from the outside to every fiber, and this T-tubule. So T-tubule totally perpendicular to all the muscle fiber. And when the action potential from the neuron comes to the muscle, and it will generate the muscle's action potential on the surface first, then it will go through the T-tubule, and T-tubule is a perpendicular network. So it go to every fiber, and T-tubule will reach the SR and ask the SR to release calcium, trigger muscle contraction. Okay, this slide shows you the T-tubule. So all the T-tubule perpendicular to the muscle fiber, and they can quickly transduct the electrical signal to every muscle fiber. And T-tubule connect to the SR through terminal cisterna. So this part, the connecting part of the SR to the T-tubule is called the terminal cisterna. And when the signal comes from the surface through the T-tubule, it will connect to the terminal cisterna. Through the terminal cisterna, it goes to the whole SR. And SR is a container for calcium, so calcium will be released, and calcium will trigger the muscle contraction. There's the thick filament and thin filaments overlap. So behind the SR, there's the sarcolemma. There's a sarcomere. Okay, now let's look at the sarcomere structure. The sarcomere is, you find sometimes I say sarcomere because, well, that's when I took anatomy, my English was not very good. I called it sarcomere, but it's actually sarcomere. Okay. Sarcomere, they are made of thick filament and thin filaments. And the thick filaments and thin filaments, when they contract, they overlap more. That's how they make the sarcomere become shorter. And there's some terminology, like the area with thick filament only, we call it A-band. So A-bands, they have thick filaments. They look dark under the microscope. And now let's look at this part. That's made of thin filaments. But this part, they overlap. They still look dark under the microscope because of the thick filaments. So the light part under the microscope starts from here to here. So the light part under the microscope, we call it I-band. So I-band is from here to here. So I-band have thin filaments only. A-band have thick filaments, and sometimes they have thin filament as well because it's an overlapping model. And the I-band. Now let's look at this. This is called the H-zone. H-zone is the gap between two thin filaments. So when the muscle contraction happens, H-zone will become shorter because they come closer to each other, and eventually the H-zone will disappear when muscle contraction happens. And these slides show you the A-band, the I-band. So the A-band is the one look dark under the microscope, and the I-bands are the one look light. And this is called the Z-line, sometimes called the Z-disc. And this is Z line, those zigzag lines called the Z line, Z disc. And this is how the muscle fiber look under the microscope. So pretty well organized. And this is one sarcomere. You have the thick filaments, you have the thin filaments, and that's the Z disc. So from a Z disc to another Z disc, there's a sarcomere. And the dark part called the A band. So from here to here, that's the A band. And from here to here, that's the I band. And that's how they look under the microscope. So still sarcomere from the Z disc to another Z disc. And that's the A band, they look dark. And that's the I band. And that's the H zone. And now let's look at the proteins make of those, create those thick filaments and thin filaments. In the thick filaments is myosin. So myosin is the protein. And in the thin filaments, mainly those cranberry, that's called the actin. So actin and myosin, these two proteins, they naturally want to bind each other. There's like two strong magnets. They will naturally glue to each other. So it's pretty good you use the actin to make the thin filaments and myosin to make the thick filaments, because they naturally glue like two strong magnets. When they glue, muscle contraction happen. And you still need to be able to relax the muscle if you need to. So we put those those green band to cover the binding site of actin. So this is another protein called triple myosin. So triple myosin's function is to block the binding site and separate the actin and myosin. It's like two strong magnets. You put a few pieces of paper, separate them. And those pieces of paper, you separate those two strong magnets is triple myosin. So with triple myosins, and now you can have muscle relaxation. And when the signal comes to S muscle contraction, the signal is calcium. Calcium released from SR. So you need to have a calcium sensor, which is troponin. So troponin is actually a complex. So sometimes you see they call the troponin complex. It's more than one protein. And troponin is a calcium sensor. They have the calcium binding site. And when the signal comes to S muscle to contract, the calcium will bind with troponin. When the calcium binds with troponin, triple myosin shy away. Now it's like you pull those pieces of paper away from the two strong magnets, and actin and myosins, like two strong magnets, they just glue together. Muscle contraction happen. And this is when the muscle relaxed. You have a whole sarcomere, and when the muscle contraction happens, they overlap more. As I keep telling you, it's an overlapping model. So the actin and myosin overlap more. The actin and myosin its own length does not change, but they overlap more. It's like gliding window. If you think about the gliding window, that's the model. They overlap more. So when they overlap more, the whole sarcomere becomes shorter. And when the whole sarcomere becomes shorter, muscles are made of a lot of sarcomere, so the whole muscle becomes shorter. A muscle attached to bones through tendon. So they are able to pull a bone closer to the other bone and create movement. And when the muscle contraction happens, the A band does not change, because A band is where the thick filaments, the thick filament create. So the A band does not change, but apparently the I band become much shorter, because I band is the areas you have thin filament only. And when these two filaments overlap more, you definitely have less thin filaments only area. So the I band becomes shorter, but A band remain the same. And H zone, you can find the H zone disappear. So this show you that's the gliding model. When the muscle contraction happen, the A band remain the same, the I band gets shorter, and H zone becomes shorter or disappear. and the whole sarcomere becomes shorter. And these are the animation. I'll leave those videos to you. Antician and nibulum, I don't emphasize these two too much in this class. These are the proteins help to stabilize the actin and myosin. Motor unit. So motor units are the muscle fiber and the neuron. Each neuron, motor neuron, innervate. So every time you see the word innervate, means it touch. The neuron touch the muscle fiber. It can touch other neuron, also called innervation. And the motor neuron, this motor neuron plus all the fibers that motor neuron innervate is called motor unit. And you can have a small motor unit like the red motor neuron innervate 4 fibers, and this blue motor neuron innervate 2 fibers. They are all small motor unit. But you can have a big motor unit, like the neuron innervates 100 or 1,000 of fibers, and they all have different functions. Small motor units are good for fine-tuning movement. So like your finger, your face muscle, those are small muscles. They create delicate movement. You need small motor unit. In your back, your leg, these muscles are big motor unit muscle, and their function are different. They can maintain the posture and create movement. So you need to have a small motor unit and big motor unit. They have different functions. So again, they show you the motor unit. So that motor neuron plus all the fibers that neuron innervate is motor unit. And the signal comes from the neuron. It will ask the muscle to contract. So in our next topic, we'll talk about how they are able to transfer the signal from the neuron to the muscle. They're going to release neurotransmitter, and the neurotransmitter is called acetylcholine. And the neurotransmitter will bind with acetylcholine receptor. It's on the muscle part, the sarcolemma part. And this acetylcholine receptor will trigger the muscle's electrical signal, and in this area called the motor end plate. And that will be our next topic. Okay, let's stop here.